For this question, we're going to look at the effects of combined loading on a structure. And we have four different loads, TAP, MAP, PZ, PX, and we're attempting to figure out what the state of stress is at this location A. To start, let's go ahead and draw four cross sections. And each one of these cross sections that we've drawn will have the effect from one of the different loads. Jeff Hansen suggests this type of technique for being able to do combined loading problems. When we have this cross section as shown, there are coordinates associated with the original coordinates of the problem. So y is going to be upward, z will be to the left as originally depicted, and x will be coming out of the screen. Let's look at the contribution from px. We can draw it simply as px as an axial load coming out at us. Contribution from pz. Well, as described in the video for question 3, we can simply look at the internal transverse shear force as pz, same magnitude, same direction as the load being applied at the end of the beam. For the contribution from MAP, we'll just draw it as an applied moment here. And for the contribution from TAP, we will look at it as an applied twisting torque TAP. For the contribution from PX, we see that this is an axial load. It's treating this system as a bar, and the sigma x, the direction or the stress in the x direction, sigma x, will simply be this force divided by the area. The area is pi c squared. For the contribution from PZ, we can recognize that we have a transverse shear force acting across this cross section, and that's repetitive, acting across the section, and it's acting along the neutral axis, or along the neutral axis, it will have the highest shear stress. The maximum transverse shear stress for a beam is along the neutral axis. So A falls on that neutral axis. You may think, well, this neutral axis is vertical. Well, just rotate Z to be, in the y direction, and you'd see this is typical of what we expect for a neutral axis in a beam bending problem where the neutral axis is horizontal. So PZ also is contributing a bending moment. Now we don't know how far it is, that is from the ends of this system, but because A is on the neutral axis relative to the PZ force being applied, that means that the bending stress will be zero. So we only have to concern ourselves with the transverse shear stress. Well, the transverse shear stress for a circular cross section along the neutral axis can be given as 4/3 times the average shear stress. So what is the average shear stress? The average shear stress is just PZ divided by the cross-sectional area, right? So we know that this transverse shear stress is not going to be constant across this entire area. In fact, at a location like right here, where Z would be a maximum or Z would be a minimum, the transverse shear stress is going to be equal to 0. The XZ subscripts for this tau suggest or mean that this shear stress mimics what you see with this shear force in that it is acting on the x phase. No, x is coming out of the board, right? And it's in the z direction. So that is where we get the tau sub xz. For this problem, we continue and look at the MAP, and we say, okay, a neutral axis is now horizontal relative to the MAP. And we see that for this MAP, and maybe it's more clear on this left image, it's going to put A in compression while something down here on the opposite side of the cylinder, it would be under tension. So without even writing an equation yet, I know it's going to be a negative stress, and it's going to be in the x direction. What is its magnitude? Well, we know that the flexure formula tells us that bending stresses are going to be negative my over I. And so we get negative m app, which is the bending moment, times c, that's the radius, over I. And it's negative also just because y would be positive upward here, if we want to look at it that way. And so, or we look at it as just, okay, I need an m app times a distance from the neutral axis divided by I, and it's got to be negative because, like I said, the deformation is going to be like this. Um, the I is going to be pi over 4 c to the fourth. For our contribution from TAP, we recognize that this uh, applied torque is causing there to be twisting. And so at the center line, right along where rho would be equal to 0, right? That's where the shear stress would be 0. But as we get farther out from the torsion formula, T rho over J, we know that it's going to be max when rho equals C. So you can see that it's coming, you can see C. Now, you can see that it's going to the left here. So this transverse shear stress is interesting in that it's acting on the x face again, and it's acting in the positive z direction. Okay? So tau xz will be Tap times the rho, which is equal to C, all over J. J is going to be equal to pi over 2 c to the fourth. These expressions up here are maybe a good reminder of what their quantities are, and as I've said previously, I think of I and J as being in alphabetical order. So the I for a circular cross-section can be pi over 4, right? And J over circular cross-section can have this coefficient of pi over 2. Both are c to the fourth. So the second moment of area and the polar moment of area. Now, let's take another look at what might be happening with the stress at this location A. So I didn't do a squiggly line here, but this is, let's say, a section, and we're now at that location A. This is the x direction, and we have here a y vertically. We have also the z still going to the left. And at this location A, I can draw a little box like we see here. This box is essentially the material element that's experiencing the stress that we're describing. And so if we look now at this box from the top, all right, so x is coming out this way, z is to the left, and we have this location A, we're going to have our sigma x as we described here, and we're going to have our tau zx or tau xz, okay, on this bottom face, right? This is the x face, and it's in the positive z direction. So we see that we have tau xz here, but it needs to be balanced. So otherwise, the element would be going off to the left and accelerating. So one way to balance it is to put another arrow on the top. Another way to balance it from spinning now would be to have an element on the left, downward, and then to balance that downward force or downward stress, we're going to have an arrow on the right side going up. So once you have one arrow, you can draw all 4 arrows. So let's recap. Sigma x is going to be equal to this tensile stress minus the compressive stress that we have here. And tau xz is going to be equal to the contribution from pz, which we said was 4/3 pz over a, and also the contribution from Tap C over J from the Tap that we see here. So these are the descriptions for the stress, and we can given as the sigma x and the tau xz. We might also note that for A, the y direction normal stress sigma y is equal to 0. The z direction normal stress is also 0. The tau yz is 0, and the tau xy is also 0. Okay, thank you, and I hope you found this video helpful.